I wait for your friend attendance to the lecture. Welcome to the class. As you remember, in the previous lectures, we talked about input space partitioning or input domain modeling, especially via interface-based approach and functionality-based approach. In this session, we talk about a prominent challenge in this area, about how to choose combination values for our partitioning or our characteristics that were chosen for domain modeling. Fortunately, I have searched for good online videos for these lectures, and I find that look at this web page. This is a YouTube course which is provided by National Program on Technology and Enhanced Learning Institute from India, and a very a good lecture is provided here by a professor from India, and it is very fluent for my topic. You could use them appropriately. I send you this link, the link of the course via WhatsApp group for you to use these videos about our lectures, and you can see the topics that which taught in this course. All needed materials for our course is illustrated there, and it's according to our textbook. It was prepared based on our textbook, so it's very good for you. You can use them, especially for this chapter. You could see, you can look at these lectures. Let me see to introduce you those parts. There are many parts in this course, but at this moment, okay. We just explained this lecture for you, input space partitioning part, and in this class, in this lecture, in this session, we talk about coverage criteria according to the input space partitioning techniques, and we will illustrate an example. Also the triangle example, as you know from the previous lecture. You could use especially these three parts of this course for chapter 6. I send you links of this chapter accordingly in order to look at them. Let me first send you this link. This is the first partition that you should look at the first partition for chapter 6. The second one is this part. Then you should see this part, and after that you should look at the file at the last part has this thing. So don't worry about the concepts I will explain for you in the class. If my speaking are not so fluent, and you can use these fluent lectures for this chapter and so on for other extra chapters, as I will told you next sessions. I hope you could remember concepts as I told you in previous lectures. As you know, we talk about both approaches to modeling the input domain. Includes the interface-based approach and the functionality-based approach. In the interface-based approach, as you remember, we just consider some characteristics for our input parameters to partition the domain of that input parameter. For example, in a triangle example, we have 3 sides for each triangle, and for each side we could partition our input domain into 4 blocks according to its relative to 0 or 1 value. So you know that each side of a triangle could be greater than 1, equal to 1, equal to 0, or negative value. It's obvious that the negative value or 0 value for a side of a triangle are invalid values. It's obvious, but when we want to test functionality of a program, we should test it with invalid values, invalid inputs, as well as we should test by the valid values from its input domain. Okay, so we have 4 blocks for the first side. Again, this is the same for the second side of the triangle and third side of the triangle. So we have 16 partitions. Okay. This is just for interface-based domain partitioning. And the maximum of tests that could be held in this approach for this example is 16-4 tests, because we have 4 choices, we have 4 blocks to select a value from them for the first side, for the first characteristic for partitioning Q1. 4 choices are there for the first side, And for the second side, we have again 4 choices. And this is the same for the third side. So we have 4 product, 4 tests when we want to do complete test. Okay. As you know, we have emphasized in previous lecture this partitioning has the 2 main properties as I talked about it. The 2 properties should be hold for every partitioning is the disjointness and the completeness. This is complete for integer values. If the sides of our triangles could be only integers, this is complete. This is a complete partitioning. Okay, but when the sides could have floating point values, this is not complete, because any values between 0 and 1 is not considered in this partitioning, and we should define new partition for values between 0 and 1. However, in this case it is complete for integers. So complete only because the inputs are integers, and no any value between 0 and 1 could be used as the size of a side of our triangle. And for choosing values from each block, we simply could use boundary values. For example, when we want to choose a value from this block B1, which all elements in this block are greater than 1, the boundary value is 2. We simply use the 2 value for block B1, and it's easy for block B2 and B3 because block B2 has just 1 value, that's 1, and block B3 has just also 1 value, it's 0. So there is no choices for B2 and B3, and we simply choose 1 from B2 and 0 from B3. But in block B4 we have a lot of values to be chosen. We simply choose the boundary one. The maximum negative number, which is less than 0, is -1. So this could be these combinations, these values 2 and -1 makes a boundary conditions. We could use boundary conditions as our value selection for each block. Okay. But in a functionality-based IDM or input domain modeling, we use other characteristic or another characteristic such as geometric classification. By the geometric classification, as you know, we have just 4 classes of triangles: the scalene class, the isosceles class, equilateral class, and invalid class of triangle. You know that this block consists of all invalid combinations of three-side values for non-triangle shapes. For example, you know that all sides of any triangle could be bigger than 0, should be bigger than 0. But when we use less or equal 0 value for any side of a triangle, it's trivial that that triangle is not valid, it's not a valid triangle. So when we want to test, when we want to fail any program, we should feed it with invalid inputs as well as other valid values. So by this classification, you know we have 4 blocks, but as I told previous lecture, this could be fishy. Something is fishy in this classification or in this partitioning, because each equilateral triangle is also isosceles triangle. So these 2 blocks overlap with each other by a subset of its block. So we refine this partition. We refine this partition by geometric classification as these partitions. This partitioning. We have again scaling triangles as block 1, and the second class is isosceles triangles, all isosceles triangles but not equilateral triangles as block B2, and equilateral triangles as block BC, and invalid triangles as block B4. And for making test value, we simply use a sample or an instance of value of each block. For example, you will see in this slide, this combination for scaling triangle, this instance is not isosceles and equilateral triangle, because there is no 2 of sides be equal in this combination. This is just isosceles triangle because 2 of them are equal. The first side and the second side are equal, so this makes an isosceles triangle. And this is equilateral triangle with this same value for all 3 sides. And this is an invalid triangle because the first side plus second side is 7, and it is less than the third side. You know that for each triangle, the summation of 2 sides should be should be greater than the third side, but it's not true for this triangle, for this combination. So this combination is a invalid triangle, and we could simply check our program or test our program by these 4 test cases. Each of these is a test case for our program. So the functionality based partitioning let us to test our program with a few test cases, with just 4 test cases. Okay. there is another functionality-based input domain modeling in this slides, as you could see in this slide. Another partitioning approach or a different approach could be break the geometric characterization into 4 separate characteristics. We use each of these geometric characteristics in isolation in this approach. In this approach, we partition our domain for each characteristic in separately. For example, the first characteristic is all possible triangles are scaling triangle or not. So we have 2 blocks for this point of view. Okay, this point of view is different from the previous approach. So by this characteristic, this is a independent characteristic in this point of view. We consider all triangles into 2 parts. The first part consists of all scaling triangle, and the second part includes all non-scaling triangles. Okay, this could be done also for all other characteristics, such as isosceles characteristic, equilateral characteristic, or invalidity of triangles, valid or invalid triangles. So we have we have considered in this example 4 characteristics in isolation. For each of these characteristics, we have 2 blocks. So to test according this partitioning, we have to do at least 8. We have 8 blocks. So we have to do 8 test cases. 8 tests. Okay. But some constraint could reduce the number of tests. For example, if we test our program with an instance of this block for these characteristics, it also covers these 3 blocks, because when we have an invalid combination for a triangle, we also have not non-equilateral triangle, and this is the same for isosceles. That combination, that sample, is not also an isosceles triangle, so that instance could be located also in this part. These parts altogether could not be disjointness, because we consider each characteristics in isolation. So by this point, we could reduce the number of our test cases. By these constraints, for example, equilateral triangles, if true, that implies that it could be also isosceles triangle. Any equilateral triangle also could be located in this block, because any equilateral triangle is also an isosceles triangle. So by this constraint, when we test our program by any sample from this block, so there is no need to test again with one sample of this block, because any sample of this block, any element of this block, is also located in this plug. So by this simple notion, we could reduce the number of our test cases in this approach. Please remember, in previous approach, we test our program by just 4 test cases. But I told for this partitioning, we should use at least 8 test cases. But when we consider some more semantics of or some logics, more logics of the functionality of our program, we could reduce them again. As another example, an invalid triangle implies that the characteristics of scaling, isosceles, and equilateral be false. So when we test an invalid triangle, we also have test and a non-equilateral triangle, non-isosceles triangle, and non-scaling triangle. Okay. Let me see your messages. Can you send the link? I sent the link for you. Which link? Okay, let's go. So we can use more than one IDM when we want to test the functionality of to do functional testing of a program by input space partitioning or input domain modeling. So for every characteristic or every point of view, we can have IDM separately, and different IDMs could be used to test any program. Let me to go to the new concepts. The main problem in this area is how we can choose combinations of values. As you know, in each partitioning, such as the previous one, this partitioning, or in interface-based approach, we have several blocks that partition our input domain. But how many tests should be done? How many tests are good to be done? When we consider all combinations, there are too many tests. For example, for this simple program, if we consider all combinations for all blocks in interface-based partitioning, we should test 64 combinations. It's too many tests for this simple program. As you know, in this approach, we just test the program by 4 test cases instead of 64 test cases. The 64 test cases is very large value. Okay, so we want to talk about how to choosing combinations of values, or we have to test all combinations to test any program. Let's go and see how we could solve this challenge, how we could solve this problem. As you see, this slide says that once characteristics and partitions are defined, the next step is to choose test values. We should choose test values from our partitions or our blocks. But how choose them? How many tests should be done? So we have to use some criteria for choosing test values to choose effective subset of all combinations. There is no need to do all combinations test cases, because it would be very large number for more complex programs. In our simple program, as you have seen previous lectures, which try to detect the type of triangle, which have a few statements. When we want to test by all combinations, we should test about 64 combinations. This is a very large amount of tests for this simple program, and it could be very, very, very large for some more complicated programs. The most obvious criterion is to choose all combinations, as you have seen in previous slide, and we talk again about this in this slide. So the first criterion in input space partitioning is all combination coverage criteria. It is named ACOC. ACOC stands for all combination coverage. All combination coverage, which defines all combinations of blocks from all characteristics must be used. For example, in our triangle example, the results for our ITM based on interface-based partitioning, we have seen that this is 64 tests when we choose all combinations coverage. The number of tests is the product of the number of blocks in each characteristics. As you have seen, we have 4 blocks for each characteristic. We have seen that we have 3 characteristics. Each characteristic partitions the input values for each side of triangle. For each side of triangle, we could choose from 4 blocks. So we have the product number of blocks for each side of triangle, and we have 4 tests. This is too many tests. So all coverage combinations are not applicable, are not feasible for more complex programs. So the number of tests in this by this coverage criteria could be compute by this equation. This equation is the product of all of the number of all blocks by each characteristics. We have Q characteristics, and each characteristic I, we have via I block. So the number of tests is the product of the number of blocks in each characteristic. Okay. The second characterization of triangle, as you see before, is this, is explained via this table, and we want to show how to compute these 64 tests. Okay, so consider our partitioning, our domain modeling, as we have seen before, which is the same as this table. We have seen that we have 3 sides. Each side have 4 blocks, as explained this in this table. For simplicity, we change this table as this one. We consider each side of the triangle as a characteristic of our program. So we have 3 characteristics, A, B, and C, for our program in general. We relabel these blocks according to this naming policy. So for characteristic 1, for the first characteristic, the A characteristic, we have 4 blocks. So we could test 4 values for the first characteristic or first side of triangle, such as A1, A2, A3, A4, according to our blocks B1 to B4. And this is the same for the second and third characteristics. For side B, we could use any value of block B1, block B2, and B3 and B4 as labeled by these labels. And this is the same for side C. So if we partition or we model our input domain, such as this table, we have 16 for combinations, because when for A1, for A characteristic, we have 4 different blocks. This is the same for B and C. So let me go to the next slide and show you how all 64 tests. Look at this combination. Each of these combinations is a test case for our program. The first combination is A1 with B1 with C1, A1 B1 C2, A1 B1 C3, A1 B1 C4. And when we continue this policy to compute other combinations, we have A1 B2 C1, A1 B2 C1. This column is changed by B2. This column could be changed by B3. This column could be changed by B4. And this is the same for other collection of our combinations. As you know, none of values of block B3 or B4 are valid for triangle, because these blocks B3 and B4 define the lengths with negative or zero value for a side of triangle. And you know, we have no any triangle in the nature with a side with a less than or equal 0 side. So all of these triangles, these combinations in this column, described in this column and in this column, are invalid triangles. And we could say this the same for these two row triangles, because all of these two rows use a value from block B3 or B4 for the second side of the triangle. So all of these triangles are invalid triangles. And this is true also for these blocks. And in this block, we have also some invalid triangles, because these combinations define an invalid triangle, because this side has 0 value, because C3, this block is this one, and this one define just a 0 value as a block. So in this combinations, we have C4 or C3 value from B3 or B4 blocks. So these combinations are invalid, and this is the same for these combinations. So we have just 8 valid triangles. We have just 8. 4 of them are there, and 4 of them are. So only we have 8 valid triangles. And all other triangles displayed in this slide, all other from all 64 tests, are invalid triangles. And testing one of them is enough for our purpose. And there is no need to test any other of them. All of them are the same type, or in the same type. Okay, so all combination coverage and ACOC coverage is an exhaustive coverage, and it is not applicable for complex programs. Okay, so we should search another or other coverage criteria that could be applicable for any program. The simplest coverage criteria could be each choice coverage criteria. What's the each choice coverage criteria? The first item says that, as I said, 64 tests for triangle is almost certainly way too many. So another choice, another coverage criteria could be choice. What's the each choice coverage criteria? One criterion comes from the idea that we should try at least one value from each block. When we want to try testing one value from each block, then by 4 tests we could test each value once. Look at this table. If we test, we do the first test case as this combination A1, B1, C1. We try each value from each block of these 3 blocks once. So in each choice coverage criteria, we also want to try each choice once. So for this aim, we could simply define our test cases as these combinations. This is the first test case, this is the second test case, this is the third test case, and this is the fourth test case. By 4 test cases, by 4 tests, we could cover all possible choices. So we define each choice coverage ECC as ECC. One value from each block for each characteristic must be used in at least one test case. In at least one test case. He says that one value from each block contribute from at least one test case. So when we define the first test case as this combination, we also test the A1, one value from A1 block, one from B1 block, one value from C1. Okay, this is enough to our goal, because our goal is to try to test each block once in at least one test case. And when we define this combination as the second test case, we also have tried A2, B2 and C2 in a test case. It's enough to cover these choices. And so for the third and second, so on for the third and second partitions. Okay, so the number of tests is the number of blocks in the largest characteristics. In this example, all characteristics have the same number of blocks. So we have to test 4 combinations. The number of test cases in each choice coverage criteria is 4 in this case, because the number of the largest characteristic is 4. We have 4 blocks for each characteristic. It's possible in other programs to have characteristics with fewer blocks. So in this case, in each choice coverage criteria, the number of tests is equal with the number of blocks of the largest characteristics. In this case, all characteristics have the same number of blocks. It's 4 in this case. So we have to test 4 test cases. We have to do 4 test cases. So the number of tests is the maximum number of blocks of our Q characteristics, Q different characteristics. The maximum number of blocks define the number of our tests. As I told, these 4 test cases should be done. Any row of this box is a test case, is a test. Okay. And when we want to translate these blocks into concrete values, we just substitute each block number by a boundary value of that block. When we want to test these combinations, an instance of A1 is 2. 2 is the boundary value in A1 block. This is the same for B1 and C1. Then we want to test a triangle with A2, B2 and C2 values. We substitute each of these with a concrete value. The only concrete value in A2 block is just 1 value. This is the same for the third block. In the third block, we just consider a block with 1 value, 0 value. And in the fourth blocks, we have defined all negative numbers in these blocks. So the boundary value in this block is -1. So we defined an invalid triangle with -1 for all 3 sides. Okay. These 4 test cases cover each choice coverage criteria. Okay, because 1 value from each block for each characteristics is considered at least in 1 test case. This is a poor coverage criteria. None of these 2 coverage criteria is good for our purpose. A, C, or C, all coverage combinations, or each choice combinations. None of them are good for our purpose. Because the first one, A, C, or C, is an exhaustive testing. Is a complete testing. And there is no need to do so many tests. And on the other hand, in each choice coverage criteria, we don't grade as much as possible our tests, because we just check 1 value from each block blindly, and the relation of these blocks is not considered at all. Okay, so none of these coverage criteria are good for our purposes. We should search for other coverage criteria between these 2 coverage criteria. The first choice could be pairwise coverage criteria, which consider the relation between each 2 blocks. Each choice yields few tests. Each choice coverage criteria yields few tests. This is cheap coverage criteria and maybe ineffective, on the other hand, Another approach combines values with other values. Each block could combine each block with other blocks, all other blocks. This is a pairwise. We define the pairwise coverage criteria as PWC. A value from each block in this coverage criteria for each characteristic must be combined with a value from every block for each other characteristic. What do we mean? Please look at these test cases, which is defined by pairwise coverage criteria. When we say a value from each block should be tested with a value from every block for other characteristics, this means for our triangle example as showed in this box. So look at this test case. We define this test case as A1, B1, C1. So the combinations of A1 with B1, this combination is tested by this test case, and the combination of A1 with C1 also is tested by this test case. In the next test case, we combined A1 with two other blocks for B2 and C2, for B and C side. And this is done the same for the combination of A1 with B3 or C3, and A1 with B4 and C4. We do this again for other blocks for the site A. The A2 should be combined with every blocks for other two characteristics, such as B1, C1, C2, C3. But we know that some of them are covered in previous row. By considering the previous row, we make other possible combinations for each of our blocks. For example, for block A2, all possible combinations, pairwise combinations, is A2 with B1, A2 with B2, C2, A2 with B2, A2 with B3, A2 with B4, and this is the same A2 with C1, C2, C3, and C4. Okay. All possible combinations, all number of tests by this coverage criteria is at least the product of two largest characteristics. In this case, all characteristics have size 4. So we have 4 product 4, 16 combinations, such as explained in this box. Okay, so in pairwise coverage criteria, we try to test all pairs, all possible pairs of blocks, all possible pairs of blocks. But as you know, we have 3 parameters, and each of our test cases have 3 values. Each of our test cases tests a value from each of these 3 blocks. So each of these tests tests about 2 combination, A1 with B1, B1 with C1, 3 combinations, 3 pairwise combination, A1 with C1. Okay. This pairwise combination sometimes is few for some programs, so we could extend this pairwise to t-wise. A natural extension to pairwise is to require combination of t values instead of 2 values. Okay, so in t-wise coverage criteria, a value from each block for each group of t characteristic, must be combined. When t is all characteristics, the t-wise coverage criteria is the same as all combination. When the value of t be 2, the t-wise coverage criteria is the same as pairwise coverage criteria. Pairwise coverage criteria is a t-wise coverage criteria with the value of 2. So, and this is a natural extension for pairwise coverage criteria, and when the t value be the number of all q characteristics, the q-wise coverage criteria is equivalent to all combination coverage criteria. And when t is 2, the t-wise coverage criteria is pairwise coverage criteria. Okay. And this last item says that t-wise is expensive for large numbers of t, and benefits are not clear. Why benefits are not clear? Because we combine these characteristics in groups of t characteristics blindly, and we don't consider any meaningful relationship between these t characteristics. We just make groups of characteristics of size t with no considerations of the meaning of those characteristics. And this grouping is done blindly, and so the benefits of t-wise coverage criteria are not so clear. Okay. Another approach could be use base choice coverage criteria. In base choice coverage criteria, we choose some combinations according to the meaning of their characteristics. Let me see your message. Okay, there is no important message. Testers sometimes recognize that certain values are important in a specific program by the using of domain knowledge. When we consult with a domain expert, we can recognize some certain values have more importance. So we should test that those important values in our testing process. So based on this point of view, we could define some basic inputs as base choices of our testing process. So this box defines formally base choice coverage criteria as BCC. A base choice block is chosen for each characteristic, and a base test is formed by using the base choice for each characteristic. Subsequent tests are chosen by holding all but one base choice constant and using each non-base choice in each other characteristic. What do we mean in this definition? Let me explain this by an example. Suppose our triangle example, we have a base choice. All of us know that all of these combinations are invalid. All of us know that any valid triangle have a value for its sides greater than 1. So all of us knows that almost of our tests should be chosen from this area and not in this area. This area has less importance, and this area are more important in our case. This notion is kept by our domain knowledge. So we want to define a combination from this column as our base choice test. So according to this labeling table, we define this combination as our base choice for our test cases. Then we test this combination with any other values from other blocks. Let me go back. Okay. For example, in one test, in each of the other tests, we change a value from just a block. For example, we test A1 B1 with C2. We test A1 B1 with C3. We test A1 C1 with B2. So we consider all choices be constant except one of them in each test. In each other tests, we just change one of this block and we keep all other constant as defined by our base choice. Our base choice, as I said, is this combination, and in each other test we simply change one of these values. Let me go back to our slide. Base choice. So when we define these combination as our base selection or base choice for the triangle example, we could define according to this base choice some other tests. According to our definition, a base choice block is chosen for each characteristic. We define this part of definition according to this example. So a base choice block is chosen for each characteristic as done for this combination. For the first characteristic, base choice block is A1. For the next, for the second characteristic, the base block is B1, and for the third characteristic, the base block is C1. So a base choice block is chosen for each characteristic as done in this example, and a base test is formed by using the base choice for each characteristic. This is a base test. This is a base test. This is a base test. A base test is formed by using the base choice for each characteristic. Subsequent tests are chosen by holding all but one base choice. All but one base choice constant. In all of these tests, all but one choice is constant. For example, in these tests, A1 and B1 is the same as our base. In this test, B1 and C1 is the same as our base test. Just this choice is changed. In any of these tests, if you look at them, you see that in every of these tests, just one characteristic is changed according to our base test. Okay, so we could change this characteristic 3 more times, because for the first characteristic we have 4 blocks. One of them is selected in the base test, and 3 of them is not selected. A2, A3, and A4 is not selected at this time. So we could make 3 extra test cases by changing this first characteristic. 3 extra tests. These 3 extra tests is explained, is selected at this column. These 3 extra tests just change A characteristic, the first characteristic, from A1 to A2 to A3 to A4. And we could have 3 extra tests in which the second characteristics has different value, has different choice from different blocks. One from B2, one from B3, one from B4. This column, these 3 test cases is considered for changing the second characteristic. All other characteristics is constant. A1, C1 are constant, is the same as defined in our base test. And for the third characteristic, also we have 3 extra choices, and according to these choices we define 3 extra tests. So all the number of tests is 1 for our base test plus the sum of all other choices for our characteristics. We have Q characteristics. In this case we have 3 characteristics, and each I characteristic have BI block. One of these blocks is tested by base choice, and B minus one of them are not chosen till now. Till now, B minus one of them are not selected. So the summation of B minus one of all characteristics plus 1 is the number of our tests. For example, in this case, for these characteristics, we have 3 extra tests because we have 4 blocks for the first characteristic, and one of them is tested by base test, and 3 of them are not tested. For this characteristic, this is the same. We have 3 more blocks, and this is the same for the third. So we have 9 tests plus 1 base test in this case. So the number of tests is 1 base test plus 1 test for each other block. 1 test for each other block of each characteristic. Okay. Base choice nodes. There are some consideration to select the base test or select the base choice. As I told you, for this example, all of us know that the sides of any valid triangle should be greater than 1. So we select our base choice from blocks A1, B1 and C1. This should be kept from business knowledge or domain knowledge. Base choices can be most likely from an end use point of view. some choices are likely for end users to test. So base choices could be selected by the consulting with our end users. Another notion is that we use the simplest combination as base choice, or smallest combinations, smallest values as our base choice. When we choosing values according to relative of values to a special value such as 0, we could use the 0 value for all blocks as our base choice, because the relation to 0 is important in our point of view. Okay. Or another condition or another consideration could be first in some ordering. For example, when we consider values larger than or greater than 1 is can make any blocks, so we consider the smallest value in that block, as you have seen 2 for our triangle example. And there are some other considerations. You could use them to choose base choices. Let me see the clock. There is no any times in this session. Yes, we can't understand more. You need a rest. Be comfortable. Let me quickly explain two other to quickly explain another coverage criteria and finish the class. You can see the videos introduced at the first of this session for more explanation, for more illustrations. Another extension for base choice could be multiple choice. In some programs, for example, in our triangle, we could have more than one base choice. So we could define multiple base choice. This is a natural extension for base choice. If you read this, if you can notice the previous coverage criteria, you could learn about this multiple choice easily, and there is no need to more explanation. For example, in this in our triangle case, we have defined two base choices, and according any of these base choices, we could define extra tests for consider two of these characteristics constant and change one of them. One of them could be changed by two other blocks, because we have two base choice, and two of these blocks for B1 and for block B is tested. B1 and B2 are tested, so any other extra tests could be made by block B2 and B3 and B4. You could see this from this column, and this is the same for other characteristics, and this is the same for another base choice. This chart shows the subsumption relation between all the 6 coverage criteria explained in this session. At the top of them, we have all combination coverage criteria. At the bottom of them, we have each choice coverage criteria. As you have seen in this session, all combinations consider all possible tests, and each choice is the smallest set, as you've seen in this lecture. So there are some other coverage criteria between of these 2 criteria. At the left hand side, you could see pairwise and t-wise. As you know, as you learned, the t-wise is an extension of pairwise, and we've defined this side of this chart, and we told about the characteristics of these coverage criteria. As you know, for example, I said that we combine the characteristics of our domain modeling blindly in these 2 coverage criteria. And then we have extra knowledge about the domain of our program, about the program under test. We could use base choice or multiple choice coverage criteria as explained before, and the subsumption relation among these 2 coverage criteria and these 2 coverage criteria are trivial, because you know that t-wise is an extension of pairwise and multiple choice is an extension of base choice, and you know that base choice can subsum each choice, and this is the same for pairwise relation with each choice. So there is no unimportant concept. You could see these 2 extra slides according to, and this slide is the summary of this chapter. Okay, no problem, be comfortable. I finish the class. Please please watch these videos. These 3 videos for these chapters, for this chapter, for the chapter of this chapter 6. This video, first of all, please look at this video, input space partitioning, labeled by input space partitioning. The second video you should see is the input space partitioning coverage criteria, and the third one is this video. Please note that in this 2 video, another simple example is considered, and the concepts are defined according to that simple example, and finally the triangle example is explained in this video. So please look at these videos more deeply before the next session. Let me